Hello and welcome to the sleepy god. Rain, a simple word, yet one that carries with it the weight of the world. It falls so often, so predictably, that we scarcely pause to marvel at it. But what if we did? What if, for just a moment, we allowed ourselves to wonder at the intricate chemistry, the invisible dance that turns water vapor into life-sustaining droplets? When the rain taps on your window or falls softly on your face, it's not just water, it is the quiet work of nature, a silent conversation between the sky and the earth. The process behind every drop of rain is as fascinating as it is hidden. Every raindrop is born not in the clouds themselves, but in the unseen corners of the atmosphere, a place where tiny particles of dust, salt, and pollen come together with the delicate balance of temperature and pressure. It is here, in this invisible world, that the story of rain begins, a story of transformation, of molecules that shift and dance, of interactions so subtle that we often miss them. But behind every drop that falls from the sky is a tale of chemistry and life, an ancient process that continues, largely unnoticed, as it shapes the world around us. To truly understand rain, we must first understand its chemistry. We often think of rain as pure, as if it simply falls from the sky in its clean, distilled form. But in reality, each raindrop is a cocktail, a mixture of water, dust, gases, and even microscopic life. This is where the beauty of rain lies, in the complexity of the process that turns vapor into liquid, in the delicate interplay of forces that create each droplet, and in the quiet yet profound impact that each raindrop has on the world. Every time rain falls, it brings with it more than just moisture. It carries with it the memory of the atmosphere, the particles that it picks up along the way, and the gases that dissolve into it. The rain is a mirror of the air. It passes through a snapshot of the world above us, captured in each tiny droplet. From the smallest microbe to the largest forest, rain is a carrier of life, of change, and of energy. It sustains ecosystems, nourishes plants, and even helps shape the land itself. And yet, despite all its grandeur, rain remains a quiet miracle. It falls without fanfare, slipping unnoticed into our daily lives. But when we stop to listen, when we pause for a moment to understand the science behind it, we begin to see rain in a new light. It is more than just water falling from the sky. It is a dynamic, ever-changing chemical process that connects the earth and sky. And in doing so, it connects us all. So next time the rain falls, don't just let it wash over you. Take a moment to appreciate the journey that brought each droplet to the ground, from the evaporation of water to the condensation that forms clouds, from the birth of droplets around dust particles to the eventual descent to the earth below. Every raindrop is part of a larger story, a story of chemistry, of nature's endless cycles, and of life itself. Imagine the vastness of the oceans, the serene surface of lakes, or the rhythmic ebb and flow of rivers. Above them, something is always happening, a constant exchange between water and air. It's a quiet process, invisible to the naked eye, but crucial to the existence of rain. This is evaporation, the transformation of water into vapor, a journey that begins on the surface of bodies of water but extends far beyond. Evaporation is the quiet escape of water molecules from their liquid form into the invisible realm of the atmosphere. Picture a warm summer day by the ocean. The sunlight shines down, warming the surface of the water. As the temperature rises, water molecules at the surface begin to move faster, gaining enough energy to break free from the liquid and slip into the air as vapor. This is the start of the water's long journey. The same thing happens on a smaller scale every time a puddle shrinks under the heat of the sun, or a damp shirt dries on a clothesline. What we often overlook, however, is the scale of this process. While we may not notice it happening, water is constantly being lifted from the Earth's surface and into the sky. Every body of water, from vast oceans to tiny streams, is contributing to this invisible flow of water vapor. The key to evaporation lies in temperature. The warmer the water, the faster the molecules move, and the more likely they are to break free. In tropical regions, where the air is already heavy with moisture, evaporation happens in a constant, ceaseless rhythm, feeding the atmosphere with the water vapor that will eventually return as rain. Even in cooler climates, this process still occurs, albeit more slowly, but it is no less important. Think of the vast tropical oceans, where evaporation is at its peak. These bodies of water act as the lungs of the planet, releasing massive amounts of vapor into the air, fueling weather systems that stretch across continents. Even in cooler places, rivers and lakes are continually losing water to the atmosphere, feeding the clouds that will bring rain to the land. As the vapor rises, it moves up through the layers of the atmosphere, carried by winds and air currents. But in this upward journey, the water does not stay in its vapor form forever. Eventually, the vapor will cool, and condensation begins to take place. The higher the altitude, the colder the air becomes, causing the vapor to slow down and condense into tiny droplets. This is where the next phase of rain's creation begins, a transformation that will eventually lead to the formation of clouds. As the vapor rises through the atmosphere, cooling and clustering together, something remarkable is happening in the unseen depths of the sky. While we often think of clouds as these vast, fluffy masses, they are, in truth, vast suspensions of countless microscopic droplets, each one a product of a subtle but crucial process known as nucleation. Imagine the air as a vast ocean, constantly moving and shifting, carrying within it tiny particles, grains of dust, specks of salt, and even the occasional trace of volcanic ash. These particles, which we often overlook in our day-to-day lives, are the unsung heroes of the rain cycle. They are the seeds, the foundations around which water vapor can gather and begin to form droplets. This is where the magic of nucleation begins. When water vapor meets these tiny particles in the air, something remarkable happens. The water molecules, which have been floating freely in the atmosphere, are attracted to these particles, clinging to them as if they were magnets. The forces of molecular attraction cause the water molecules to gather, first into a small film of liquid that begins to grow, and then into a fully formed droplet, what might seem like an insignificant grain of dust or a fleeting puff of sea. Salt becomes the starting point for a new raindrop. Without these particles, the atmosphere would struggle to form rain at all. In fact, scientists have even created laboratory conditions where water vapor refuses to condense unless it has anything to cling to. The absence of these particles, or cloud condensation nuclei, prevents condensation from occurring altogether. It's a curious and counterintuitive truth. The very impurities we sometimes call pollution or dirt are, in fact, essential for rain. But not just any particles will do. The process is delicate. For nucleation to occur, the particles must be small enough, and the environment just right. Too few particles and the vapor can't form enough clusters to create droplets. Too many, and the droplets might not have enough space to grow. The particles provide the necessary scaffolding, the starting point for the droplet's journey. Once the droplet begins to form, it isn't yet a raindrop in the traditional sense. It is still a tiny cluster of water molecules clinging to a particle no bigger than a pinhead. Yet, in this microscopic stage, the birth of a raindrop is already underway. Each droplet is a tiny alchemist, transforming invisible vapor into something tangible, ready to begin its journey toward Earth. The journey from water vapor to liquid is not a simple one. It requires a precise balance of temperature and pressure forces that act upon water molecules to bring them together, transforming them from an invisible gas into the visible droplets that we see suspended in the sky. It is in this delicate process of condensation that the character of a raindrop truly begins to take shape. At higher altitudes, the temperature drops, and the cooler air provides the perfect environment for condensation to occur. As water vapor rises through the atmosphere, it encounters progressively colder temperatures. The molecules slow down, losing some of their energy, and begin to bond with one another. It's as if the vapor is reaching its limit. Its transformation from gas to liquid is imminent, but only under the right conditions. The process begins subtly. As the vapor cools and condenses around the tiny particles like dust or sea salt, it forms microscopic droplets. These droplets are so small that they remain suspended in the air, floating gently in the cloud, caught between the forces of gravity pulling them downward and the upward air currents keeping them aloft. They dance in the air, merging, growing, and occasionally evaporating back into vapor as the temperature fluctuates. This constant push and pull, this balancing act between temperature and pressure, creates the dynamic and ever-shifting world of clouds. The higher the altitude, the colder the air, which makes condensation more likely. This is why we see towering clouds, great, majestic formations in the sky where warm, moist air rises and expands. But it isn't just the cold that matters. The pressure in the atmosphere also plays a critical role. In the lower pressure of the upper atmosphere, water molecules can stick together more easily. If the pressure were higher, these molecules would be constantly torn apart, and condensation would not happen so smoothly. As the droplets grow larger, they begin to collide with one another, merging and increasing in size. What once started as a tiny particle surrounded by a film of water becomes a larger droplet, but still it is not quite ready to fall. The air currents within the cloud keep the droplets suspended, jostling them around like dancers in a ballroom. Some droplets evaporate back into vapor, while others continue to grow as they collide with more moisture. It is this process of condensation that forms the very essence of a cloud. Far from being a static mass, a cloud is a constantly changing collection of millions, if not billions, of these tiny droplets. And the longer the droplets remain suspended, the larger they grow, until they become too heavy for the air to hold them. The moment these droplets reach a certain size, the forces of gravity take over, and the rain begins. But the creation of each raindrop is a delicate and complex process that begins long before the first drop falls to earth. It is a dance of temperature, pressure, and moisture, a chemical choreography in the sky, guided by the invisible rules of physics and chemistry. As droplets grow larger, they begin to merge, creating the dense, fluffy masses we call clouds. A cloud is not the uniform mass of cotton that it may appear to be from below. Instead, it is a dynamic and complex suspension of countless tiny droplets, each one suspended in the air by the invisible forces of rising warm air and cooling atmospheric pressure. The cloud may seem still from a distance, but within it is a constant unseen motion, a shifting mass of droplets colliding, merging, evaporating, and condensing. These clouds are in constant flux. The droplets, which began their lives as tiny water molecules clinging to particles of dust or salt, now come together in increasingly larger clusters. As more water vapor condenses onto these droplets, they grow. In fact, each droplet is in an ongoing process of transformation, constantly changing size as it interacts with its neighbors. Some droplets may merge into larger ones, while others might evaporate back into the air if conditions shift. This is the restless, never-ending dance of the cloud. One of the most fascinating aspects of cloud formation is how the droplets interact with one another. Droplets that are close to each other in size will often collide and merge, growing larger and larger until they reach a size where the air currents that once kept them suspended can no longer do so. The merging process accelerates as the droplets attract each other through a phenomenon known as coalescence. When two droplets collide, they combine to form a new, larger droplet. And this process continues until the droplets are large enough to fall from the cloud. This merging process is essential for the creation of rain. Without it, the tiny droplets would remain suspended in the cloud indefinitely, never growing large enough to overcome the pull of gravity. But as droplets merge, they increase in size and mass, eventually becoming too heavy to stay aloft. It is at this tipping point, when the droplets reach a critical size, that the rain begins to fall. A cloud, therefore, is much more than just a collection of water droplets. It is a dynamic, living system where droplets are born, grow, and eventually merge to become raindrops. And just as each droplet is a small alchemist, turning vapor into liquid, each cloud is a vast alchemical laboratory where billions of these transformations take place. For all the activity that occurs within a cloud, it is the balance between rising air currents and gravity that determines whether the cloud will produce rain. The upward force of the air, known as updrafts, keeps the droplets suspended and allows them to grow. But as the droplets grow larger, gravity begins to assert its force. Eventually, the weight of the droplets overwhelms the updrafts, and the rain begins to fall. The clouds we see in the sky are not static, but rather living, breathing entities in constant motion. Each cloud is a miniature ecosystem where water, vapor, temperature, pressure, and air currents come together to create the perfect environment for raindrops to form. And as these droplets fall, they carry with them the chemical fingerprints of the sky. They came from dust, salt, gases, and even the invisible traces of life that exist within the atmosphere. The rain is more than just water. It is the product of a delicate, invisible process that shapes not only the sky, but the world below. When we think of raindrops, most people picture a perfect teardrop shape, rounded at the bottom, tapering to a point at the top. It's an image that has been ingrained in our minds through cartoons, weather icons, and even road signs. But the reality of a raindrop is far more interesting and far more complicated than this simple, familiar image suggests. In truth, the shape of a raindrop is dictated by the forces of physics and chemistry, and it doesn't follow the elegant teardrop curve we so often imagine. Raindrops are subject to surface tension, gravity, and air resistance, all of which play a role in shaping them as they fall through the atmosphere. At the heart of a raindrop's shape is surface tension, the force that acts at the surface of a liquid, pulling the molecules together. Water molecules at the surface of a droplet are pulled inward by the cohesive forces between them, creating a sort of skin that tries to minimize the exposed surface area. In the case of tiny droplets, this surface tension is strong enough to create a nearly perfect sphere. In smaller droplets, such as mist or dew, the surface tension dominates, and the droplets remain beautifully round. This is why raindrops appear spherical. When they are small, there is not enough force from gravity or air resistance to distort them. However, as raindrops grow larger and begin their descent through the air, the physics changes. Once droplets reach a size of around 2 millimeters in diameter, they no longer maintain their perfectly spherical shape. Gravity starts to play a more significant role. As the droplet falls, air resistance pushes against it, creating drag that flattens the bottom of the droplet. This causes the raindrop to take on the shape of a hamburger bun, flat on the bottom and rounded at the top. This is the most common form for medium-sized raindrops. But the story doesn't end there. As raindrops grow even larger, they encounter even more resistance from the air. The force of gravity begins to outweigh the surface tension, causing the droplet to flatten further. At about 4 millimeters in diameter, the raindrop can take on an almost parachute-like shape, with a flat bottom and a slight indentation at the top. Larger droplets, especially in intense rainstorms, may even split apart mid-air due to the sheer forces acting upon them, fragmenting into smaller droplets before they reach the ground. This process, where raindrops lose their perfect spherical shape and become distorted, is one of the many fascinating aspects of rainfall. It is a reminder that nature does not always follow the patterns we expect or imagine. The graceful teardrop shape is, in fact, a myth, a simplification that is far from the truth. Raindrops, like all phenomena in nature, are governed by complex forces, and their shapes tell a story of the balance between cohesion, gravity, and air resistance. Beyond just their physical shape, the size and formation of raindrops also influence how they interact with the world. The size of a raindrop affects its speed as it falls, the amount of water it carries, and even the sound it makes when it hits the ground. Larger drops hit with more force, creating a louder patter, while smaller droplets produce a softer, more delicate sound. The architecture of a raindrop, from its size to its shape, influences how rain behaves and how we experience it. But there's more to the raindrop than its shape. The surface tension that gives the raindrop its form also plays a key role in how it interacts with light, which is why raindrops are essential in the formation of rainbows. Each droplet acts like a tiny prism, bending and scattering light to reveal the full spectrum of colors hidden within sunlight. In a way, the raindrop's shape and size determine not only its physical properties, but also how it communicates with the world around it. From the sound it makes to the light it bends. The raindrop's physical structure is part of a much larger story, a story written in the language of physics, chemistry, and light. Few experiences are as universally recognized as the scent of rain. The air feels different, cleaner, fresher, as if the earth itself is taking a deep breath. This fragrance, so distinct and comforting, has a name, Petrichor. It's a term that evokes nostalgia, calm, and even a sense of renewal. But what is it that makes the smell of rain so captivating, and how does this earthly perfume come to be? The answer lies in the subtle, almost invisible chemistry that occurs when rain hits dry soil. Before a storm, during dry spells, plants excrete oils that are absorbed by the soil and rocks. These oils serve several purposes for the plants. They protect seeds, deter unwanted vegetation, and help regulate growth. Yet, when the rain finally falls, these oils, now trapped in the earth, are released into the air. As the water droplets make contact with the ground, they break these oils free, sending them rising into the atmosphere, where our noses pick up their distinctive scent. But it's not just plant oils that contribute to the smell of rain. The earth itself holds another key player, geosmin. This compound, whose name is derived from the Greek words for earth and smell, is produced by soil-dwelling bacteria, especially these microorganisms thrive in the soil, breaking down organic matter and recycling nutrients. When the rain disturbs the soil, it releases geosmin into the air, a scent that many describe as earthy, musty, or even sweet. Geosmin is remarkable. In its potency, humans can detect it in concentrations as low as a few parts per trillion. To put this in perspective, it's like being able to taste a single drop of something in a large swimming pool. This compound's presence gives rain its characteristic earthy aroma, especially after a dry spell, when the ground has been particularly thirsty for moisture. The combination of these compounds, plant oils and geosmin, creates the unmistakable scent we associate with rain. The aroma, while subtle, is powerful enough to trigger memories, evoke emotions, and stir a deep sense of connection to nature. For some, it recalls childhood moments of playing outside just before a summer storm, or the soothing rhythm of rain falling on the roof during a quiet night. There's another scent that sometimes accompanies rain, particularly during thunderstorms: ozone. Ozone is a molecule made of 3 oxygen atoms, and it forms when lightning splits the oxygen molecules in the atmosphere. This process, called ozone generation, produces a sharp, almost metallic smell that many people notice in the air just before or during a thunderstorm. Although ozone is unstable and doesn't linger for long, its presence adds an electric quality to the scent of rain, enhancing the sense of energy and anticipation that thunderstorms often bring. What makes rain's scent even more intriguing is that it can vary depending on the environment and the type of rain. For instance, the rain in a forest might carry a different scent than rain in a city, as the microbial life, plant oils, and minerals differ. A light drizzle in a rural area might bring a subtle fragrance, while a heavy downpour in an urban setting might intensify the smell, picking up pollutants and dust along the way. The scent of rain, then, is not only a complex blend of chemistry, but also a sensory experience deeply tied to the natural world. Each rainfall is a unique composition, a fleeting moment of nature's perfume, shaped by the environment it falls upon. This is why the smell of rain can feel so personal, so intimately connected to the place and time in which it falls. For many, the scent of rain is a reminder of nature's cyclical rhythms, a sign that the earth is alive, constantly renewing itself. It's a fragrance that reassures, refreshes, and even inspires. But more than that, it's an ever-present connection to the earth and the forces that shape it, a subtle yet profound reminder of the invisible chemistry at work in our world. A thunderstorm is one of nature's most dramatic performances, a cacophony of lightning, thunder, and torrential rain. The sky darkens, clouds swell, and the air is charged with energy. But within the flash of lightning, hidden beneath the roar of thunder, lies a subtle yet crucial chemical process that plays an important role in enriching rain and nourishing the earth below. Lightning, with its incredible power, is far more than just a spectacle. Each flash is a highly energetic event, reaching temperatures hotter than the surface of the sun, around 30 degrees Celsius. In this intense heat, the gases in the atmosphere undergo a dramatic transformation. Nitrogen and oxygen, which normally exist in stable pairs, are torn apart by the energy of the lightning strike, splitting into individual atoms. These newly freed nitrogen and oxygen atoms are highly reactive, and almost immediately, They combine to form nitrogen oxides, such as nitric oxide NO and nitrogen dioxide NO. These nitrogen oxides, once created, mix with the rain that follows, dissolving into the droplets and reacting with the water to form nitrates, one of the most important nutrients for plants. This phenomenon is vital for life on Earth. Nitrogen is an essential element for all living organisms. It is a key component of amino acids, proteins, and DNA. While the atmosphere is made up of about 78% nitrogen gas, NMS, this nitrogen is locked in a stable form that plants and animals cannot use directly. They require nitrogen in a more reactive form, such as nitrates, to build the complex molecules necessary for life. In this way, lightning provides a natural form of nitrogen fixation, breaking the tough nitrogen bonds and transforming atmospheric nitrogen into a usable form for plants. Each lightning strike then acts like a small fertilizer factory. It produces nitrates that fall to the earth with the rain, enriching the soil and supporting plant growth. This is one of nature's oldest processes, predating even human agricultural practices. For early ecosystems, long before humans developed the technology to create artificial fertilizers, lightning was an essential part of the nitrogen cycle. It ensured that nitrogen, a nutrient critical for life, was available to plants, which in turn supported the rest of the food chain. The role of lightning in fertilizing the earth through the creation of nitrates is significant not only for plant life but also for ecosystems at large. These nitrates, once they reach the soil, help plants build the complex structures they need to grow, produce seeds, and propagate. As plants absorb nitrates, they pass them along the food chain, enriching the entire ecosystem. But lightning's impact doesn't stop there. It also contributes to another important atmospheric compound, ozone. As the lightning splits oxygen molecules in the atmosphere, some of the fragments recombine into ozone OV. Although ozone is typically associated with the protective layer in the upper atmosphere that shields Earth from harmful ultraviolet radiation, it can also form near the ground during thunderstorms. The ozone generated by lightning is and its presence in the air often manifests as the sharp, metallic scent we associate with thunderstorms. It is a fleeting compound, existing only briefly before it breaks down. But it plays a role in cleaning the atmosphere and also adds to the dramatic atmosphere of a thunderstorm. The combination of nitrates and ozone in the rain, created by the electrical power of lightning, makes thunderstorms far more than just dramatic weather events. They are, in essence, nature's active agents of fertilization and purification in this way. Each storm is not only a harbinger of rain, but also a powerful agent of transformation, enriching the soil, replenishing nutrients, and contributing to the natural cycles that sustain life. The energy of lightning, the chemistry of rain, and the renewal of the earth all come together in a spectacular, ever-repeating cycle that has been going on for millennia, long before humanity ever witnessed its grandeur. For much of human history, rain has been regarded as a natural, beneficial event, a replenishment of the earth, a giver of life. However, as industrialization took hold, a darker side of rain emerged: acid rain. While rain has always carried a slight acidity due to the presence of dissolved carbon dioxide, it wasn't until the rise of human activity, especially during the Industrial Revolution, that this acidity took on a dangerous, destructive form. The process behind acid rain begins with the release of sulfur dioxide and nitrogen oxides NOx into the atmosphere, primarily from the burning of fossil fuels, such as coal and oil. In the 18th and 19th centuries, as coal became the dominant source of energy, power plants, factories, and households began emitting vast quantities of sulfur dioxide into the air. In heavily industrialized cities, like London and Manchester, this pollution mixed with the rain, creating a highly acidic mixture. The sulfur dioxide reacts with water vapor in the atmosphere to form sulfuric acid HSOs, and nitrogen oxides combine with water to form nitric acid HNOY. This resulted in rain that had a pH significantly lower than natural rainfall, often dipping to levels as low as 3 or 4. The impact of acid rain was profound and destructive. On the surface of the earth, acid rain eroded buildings, monuments, and statues, leaving a visible mark on human history. The sulfuric acid in the rain would react with calcium carbonate in marble and limestone, dissolving the stone and eating away at inscriptions and delicate carvings. Even statues, once proud and immovable, were worn down by the constant assault of acid rain. Some of the grandest monuments in the world, including parts of the ancient ruins and works of art, were permanently damaged, their details blurred or lost entirely. Acid rain did not only affect human creations, however, it had a far-reaching and devastating impact on the natural world. Forests, which rely on balanced nutrients in the soil, were severely impacted. Acid rain leached away vital minerals like calcium and magnesium from the soil, making it difficult for trees to grow and thrive. At the same time, it liberated toxic elements like aluminum from the soil, which then poisoned the roots of trees, weakening them further. Entire forests, once lush and green, began to wither and die, leaving behind barren landscapes. In aquatic ecosystems, acid rain caused even more harm. When the rain fell into lakes and rivers, it lowered the pH of the water, making it more acidic. Many aquatic organisms, including fish, struggle to survive in waters with a pH too far from neutral. Acidic water interfered with the ability of fish eggs to hatch, and the high acidity killed or severely harmed fish populations. In some lakes, fish populations completely collapsed, and entire aquatic ecosystems were destroyed. The devastating effects of acid rain prompted scientific inquiry, especially as the problem seemed to extend beyond national borders. In the mid-century, researchers in Scandinavia began noticing that lakes were becoming more acidic, even in regions far from major industrial centers. They discovered that the pollutants causing acid rain could travel great distances in the atmosphere, carried by winds across borders and continents. This realization shifted the issue from a local environmental problem to a regional, even global, one. By the late 20th century, the effects of acid rain were becoming increasingly apparent, and the need for action grew urgent. In response to growing concern, many countries began to take action, enacting environmental regulations and policies aimed at reducing emissions of sulfur dioxide and nitrogen oxides. Technologies like scrubbers, which remove sulfur from the exhaust gases of power plants, were introduced to capture pollutants before they could reach the atmosphere. The use of cleaner fuels, such as natural gas, helped to reduce the overall amount of sulfur dioxide being released. Additionally, the introduction of catalytic converters in cars dramatically reduced nitrogen oxide emissions. The results of these efforts were encouraging. Over time, emissions of sulfur dioxide and nitrogen oxides began to decrease, and the effects of acid rain began to recede in many parts of the world. Lakes that had once been acidic started to recover, with fish populations slowly rebounding as the waters returned to more neutral pH levels. Forests, too, began to show signs of renewal as the soil regained some of its lost nutrients. But the story of acid rain is not just one of environmental harm. It is also an example of how scientific understanding and collaboration can lead to solutions. The recognition of acid rain's destructive power spurred global cooperation, leading to changes in policy, technology, and industry practices. What started as an environmental crisis became an opportunity for progress, proving that understanding the science behind the problem is the first step toward fixing it. However, acid rain's legacy is far from gone. Though the worst effects have been mitigated in many parts of the world, the damage to ecosystems and structures still lingers. Even with improvements in air quality, some areas continue to struggle with the after-effects of decades of pollution. The story of acid rain is a cautionary tale, a reminder of how human activity can disrupt the natural balance and leave lasting scars on both our planet and our history. When we think of thunderstorms, we often imagine dramatic flashes of lightning, booming thunder, and torrents of rain. But beneath the violence of a storm lies a quieter, yet equally significant, contribution to the natural world, the enrichment of the soil. As intense as thunderstorms can be, they serve a vital role in the ecosystem, acting as natural fertilizers for the soil. This unexpected form of nourishment begins with the lightning strikes that frequently accompany these storms. We've already explored how lightning splits nitrogen molecules in the air, transforming them into nitrogen oxides. When these nitrogen oxides dissolve into the rain, they react with water to form nitrates compounds that are essential for plant growth. This process of nitrogen fixation, once solely the domain of soil-dwelling bacteria, has now been augmented by the power of lightning. As the storm rains down, these nitrates fall to the ground along with the rain, carried through the atmosphere to the soil. This delivery of nitrogen is critical for plants, which rely on it to produce amino acids, proteins, and other essential compounds necessary for their growth. Plants cannot use nitrogen directly from the atmosphere because it exists in an inert form as N. Instead, they require nitrogen to be fixed, or converted into more reactive forms, such as nitrates or ammonium. Lightning, with its immense energy, provides the spark for this process, converting atmospheric nitrogen into a usable form that plants can absorb through their roots. This contribution to the soil is not just a bonus, it is vital to the cycles of life that sustain ecosystems. In the early days of life on Earth, long before humans learned how to produce fertilizer, storms played a critical role in distributing nitrogen across the land, fertilizing ecosystems that had no access to industrial inputs. The nitrates delivered by thunderstorms supported plant growth, which in turn supported herbivores, carnivores, and everything else in the food chain. Beyond the nitrates, thunderstorms also indirectly benefit the soil in other ways. The heavy rainfall associated with storms helps to wash away the buildup of salts and minerals that might otherwise accumulate on the surface of the soil, especially in arid regions. In some areas, the storm acts as a natural cleansing agent, replenishing the soil with fresh water, while washing away pollutants or excess minerals that could harm plant life. Thunderstorms also help to create favorable conditions for plant growth by enhancing soil aeration. When the rain falls heavily, it not only moistens the soil but also breaks up compacted layers, allowing oxygen to reach the roots of plants more easily. This is particularly beneficial in regions where the soil has become too compacted due to drought or human activity. As the rain saturates the ground, it creates spaces between soil particles, improving root health and nutrient uptake. In the immediate aftermath of a storm, it's easy to see the impact that rain has on the land. Plants seem to perk up, their leaves glistening with moisture as they absorb the life-giving water. This rapid transformation is often more than just the hydration from the rain itself. It's the result of a delicate dance of nutrients, chemical compounds, and energy brought down from the sky. Thunderstorms, despite their chaotic and often frightening appearance, are not just destructive forces of nature, they are a crucial part of the nutrient cycle that sustains life on Earth. Their chemistry, from nitrogen fixation to soil aeration, makes them the planet's natural gardeners, fostering the growth of plants that feed not just animals, but the very ecosystem that relies on them. The next time you find yourself caught in the midst of a storm, take a moment to consider the quiet gifts it offers to the earth below. When we think of rain, we often imagine it as a simple event, water falling from the sky to nourish the earth. But rain serves another, often overlooked, purpose. It acts as nature's atmospheric cleaner. Each drop that falls from the sky has a role in purifying the air, removing pollutants, dust, and other particles that have accumulated in the atmosphere. This cleansing process, known as washout and rainout, helps to reset the balance of the environment, making the world feel fresher, clearer, and more vibrant after a storm. The cleaning begins long before the raindrops touch the ground. As water vapor rises and condenses into droplets, it captures particles from the air. These can include anything from natural elements like sea salt and dust to pollutants like soot, smoke, and industrial emissions. In essence, the raindrop acts like a tiny vacuum cleaner, gathering all the microscopic debris suspended in the atmosphere. As the droplets form and grow, they collect these particles, pulling them down to earth when the raindrop finally falls. This process helps clear the air of pollutants that would otherwise remain in the atmosphere, contributing to smog, haze, and poor air quality. But the cleaning doesn't stop there. Once the rain begins to fall, it continues its work of scrubbing the air. As raindrops tumble through the atmosphere, they encounter even more particles, such as pollen, dust, and pollutants released by human activity. These particles, whether they are natural or man-made, are captured by the falling droplets and carried back to the ground. In a sense, each raindrop becomes a little courier, delivering these particles to the soil or water below. The effect is most noticeable after heavy rain, when the world seems to take on a cleaner, sharper quality. The sky appears more vivid, colors seem brighter, and the air feels lighter to breathe. This is due to the reduction in airborne particles that scatter light and block visibility. With fewer particles in the air, light can travel more freely, making the world look clearer. It's almost as if the rain has wiped the slate clean, leaving everything feeling refreshed. The impact of this cleaning effect is especially important in urban areas, where the air is often thick with pollution from cars, factories, and construction. In cities, rain offers a temporary respite from the haze of dust, smoke, and other pollutants that linger in the air. It can lower levels of fine particulate matter, such as soot and tire rubber, which are known to contribute to respiratory problems. After a storm, the air feels more breathable, less oppressive, and more invigorating, a sign that nature has performed its own kind of housekeeping. In rural areas, the cleansing effect of rain may be gentler, but no less important. Rain helps to remove pollen, spores, and other natural irritants that can cause allergies and discomfort. It also washes away organic matter and dust that can build up in the environment, particularly in dry, windy regions. For farmers, this cleansing effect is beneficial not just for the air, but also for the soil. As the rain settles into the ground, it brings with it the particles it has collected, enriching the soil with nutrients, minerals, and even trace elements that might have been lacking. The process of cleaning the air through rain is not only a physical act, but also a chemical one. Water molecules are polar, meaning they have a slight positive charge on one end and a slight negative charge on the other. This gives them the ability to attract and bind with a wide variety of particles and gases. Pollutants like sulfur dioxide, nitrogen oxides, and volatile organic compounds dissolve easily in water, allowing rain to efficiently capture and remove them from the atmosphere. Other particles, like dust or pollen, are simply carried along, physically swept out of the air by the weight of the rain. However, while rain can do wonders to cleanse the atmosphere, it has its limits. In areas where pollution levels are particularly high, rain can only do so much to remove harmful particles. In some cases, the very pollutants that are washed out of the air by the rain can become concentrated in the soil or in bodies of water. Acid rain, for example, which contains sulfuric and nitric acids, can have damaging effects on ecosystems when it falls in areas with high levels of industrial pollution. The rain may clean the air temporarily, but it can also redistribute pollutants in ways that harm plants, animals, and water quality. Despite these challenges, rain's ability to cleanse the atmosphere remains one of its most valuable functions. It is a reminder that even the most ordinary of events, something as common as a downpour, is part of a much larger, complex system that helps maintain balance in the environment. The next time you step outside after a storm and take in the fresh, clean air, remember that rain has done more than just water the earth. It has helped scrub the skies, removing the invisible particles that clutter the air and allowing the world to breathe a little easier. Rain's influence extends far beyond merely quenching the earth's thirst. One of its most crucial roles is enriching the soil, a process that ensures ecosystems thrive and agriculture flourishes. Each raindrop is more than just water, it is a conveyor of nutrients and minerals, transporting vital elements from the atmosphere to the Earth's surface, where they are absorbed by plants and incorporated into the food web when rain falls. It doesn't just soak the ground with moisture. It brings with it an array of minerals and compounds that help sustain plant life. These nutrients come from the rain itself, as well as from the particles it picks up along the way. As the rain falls through the atmosphere, it gathers dust, ash, sea salt, and even nitrogen compounds that have been carried on the wind. These elements, although invisible to the naked eye, are vital to plant growth and soil health. Among the most important contributions that rain makes to soil fertility is the delivery of nitrogen. While nitrogen makes up a large portion of the atmosphere, it is in a form N that plants cannot directly use. However, when lightning strikes or industrial processes release nitrogen oxides into the atmosphere, these compounds dissolve in rainwater and fall to the ground as nitrates, a form of nitrogen that plants can absorb through their roots. This process, known as nitrogen fixation, is critical for plant growth. As nitrogen is an essential building block for amino acids, proteins, and chlorophyll, in addition to nitrogen, rain can deliver other minerals like calcium, magnesium, and potassium, all of which are vital to plant health. These minerals are often found in trace amounts in the air, lifted by winds from deserts, oceans, and even volcanic eruptions. As rain falls, it collects these minerals and brings them to the soil, where they can be absorbed by plant roots and used to support growth and development. Without this regular influx of nutrients, soil would gradually lose its fertility, making it harder for plants to thrive. Rain also plays a vital role in leaching, the process by which certain minerals and nutrients are washed down into the soil, helping to distribute them evenly across the landscape. While the rain replenishes the soil with essential minerals, it also helps remove excess salts and pollutants, preventing soil degradation. In agricultural regions, this process can be especially beneficial, as it helps to maintain soil health, preventing the buildup of salts and toxins that might otherwise stifle crop growth. Another important role rain plays in soil fertility is its ability to aerate the soil. As raindrops fall, they create tiny spaces between the soil particles, allowing air to reach the roots of plants. This increase in soil aeration is especially important in clay-heavy soils, where compacted layers can block the movement of water and air, limiting the plant's ability to access vital nutrients. By loosening the soil and improving its structure, rain enables plants to root more deeply, take in more nutrients, and thrive. For farmers and gardeners, this connection between rain and soil fertility is evident every time crops grow taller after a storm. It's not just the water that's important, it's the cascade of nutrients and minerals that accompany it. In regions where rainfall is seasonal or sparse, the impact of a good rainstorm can be transformative, turning barren land into fertile soil, ready for cultivation. Rain, in this sense, is not just a natural event, but a life-giving force that ensures the continued vitality of our planet's ecosystems. However, rain's role in soil fertility is not without its challenges. Too much rain can lead to erosion, where the soil is washed away before it has a chance to hold onto its nutrients. In areas where heavy rainfall is common, erosion can strip away topsoil, leading to a loss of fertility and making it difficult for plants to grow. In such cases, farmers and land managers must take steps to manage water flow and prevent the soil from being washed away. On the other hand, areas with insufficient rain can suffer from drought, which hampers plant growth by limiting the availability of water and nutrients. Without regular rainfall, soil can become dry and compacted, making it harder for plants to access the nutrients they need. Droughts can lead to crop failure and desertification, where once fertile land becomes arid and barren. Despite these challenges, rain remains one of the most powerful natural forces in maintaining soil fertility. It nourishes the earth, replenishing the nutrients that plants need to grow, while also helping to regulate the delicate balance between moisture, nutrients, and air. In the grand scheme of life on Earth, rain is more than just a weather event. It is a vital force in the ongoing cycle of growth, decay, and renewal that sustains life on our planet. So the next time you step into a garden or walk through a forest, consider the quiet power of rain. It is not just a gift of water, but a natural process that enriches the soil, sustains ecosystems, and ensures that life continues to flourish on Earth. Rain is a visible and essential part of a much grander system that has been at work for billions of years, the global water cycle. This cycle, one of nature's most fundamental processes, governs how water moves across the Earth, from oceans to the atmosphere, to land and back again. It is a cycle so vast, so constant, that it is often taken for granted. Yet it sustains every living organism on the planet. The cycle begins with evaporation, a process where the sun's heat causes water to escape from oceans, lakes, rivers, and even plants, turning it into water vapor. This vapor rises into the atmosphere, carried upward by air currents. Every day, the world's oceans lose millions of tons of water to evaporation, creating an invisible reservoir of moisture that fuels the water cycle. Even in cooler climates, this process occurs, though at a slower pace. But evaporation is not the only contributor to the atmospheric reservoir. Transpiration, the process by which plants release water vapor through their leaves, also plays a significant role in forests, grasslands, and wetlands. Plants are constantly breathing out moisture into the atmosphere, adding to the supply of water vapor. This combined process of evaporation and transpiration is known as evapotranspiration and accounts for a significant portion of the moisture that will eventually return as raindrop. As the water vapor rises higher into the atmosphere, it begins to cool, especially at the higher altitudes where the air is colder. The cooling causes the water vapor to condense into tiny water droplets, forming clouds. Clouds, though they may appear soft and fluffy, are in fact made up of billions of these microscopic droplets suspended in the air. As more water vapor condenses, the droplets merge and grow larger, eventually forming the raindrops that we see falling from the sky. This process of condensation is essential for the formation of clouds and precipitation. The water vapor, once invisible and scattered across the atmosphere, comes together to form a visible cloud. These clouds, depending on their size and the conditions around them, can lead to everything from light rain to massive thunderstorms. The balance of temperature, pressure, and moisture in the atmosphere dictates how much rain will fall, where it will fall, and how long it will last. Once the droplets in the clouds reach a certain size, they overcome the forces keeping them suspended. In the air, gravity takes over, pulling them down to earth as precipitation. This is when rain, snow, sleet, or hail returns to the surface, replenishing rivers, lakes, and soils. In warmer climates, this precipitation often takes the form of rain, while in colder regions, it may fall as snow or ice once on the ground. Rainwater travels through the landscape, seeping into the soil or flowing into rivers and streams. Some of the water infiltrates the ground, replenishing underground aquifers and providing moisture to plants. The rest flows over the surface, forming rivers and streams that eventually carry the water back to the oceans, where the cycle begins. Again, this constant movement of water, from ocean to atmosphere to land and back to the ocean, is the lifeblood of the water cycle. It regulates climate, supports ecosystems, and sustains life. The cycle operates on a vast scale, spanning continents and oceans, but it also works on a local level. Each raindrop that falls to the ground is part of this grand cycle, a small but vital piece of the puzzle that keeps the world's water in motion. The water cycle also plays a crucial role in climate regulation. As water evaporates from the surface of the earth, it carries heat away from the ground, helping to cool the planet. When it condenses into clouds and falls as rain, it releases that heat back into the atmosphere, warming the surrounding air. This exchange of heat helps to drive weather systems, influencing everything from gentle breezes to powerful storms. The global movement of water, in combination with the distribution of heat, shapes our weather patterns and helps maintain the balance of temperatures around the world. For humans, the water cycle is more than just a scientific phenomenon. It is a vital part of life. Our crops depend on predictable rainfall, our rivers supply drinking water, and the soil we cultivate thrives with the right balance of moisture. Without the constant recycling of water through the cycle, life as we know it would not be possible yet. The water cycle is also fragile. Small shifts in temperature, changes in atmospheric conditions, and human activity can disrupt the delicate balance of the cycle. Deforestation, urbanization, and climate change are all factors that can influence how water moves across the planet. As the world warms, the water cycle is undergoing changes, with some regions experiencing more intense rainfall, while others face longer droughts. These shifts affect not only ecosystems, but also human populations that rely on steady rainfall. For agriculture, drinking water, and industry. Rain, in this context, becomes more than just a natural occurrence. It is part of a larger, interconnected system that binds together the forces of nature, sustaining life across the planet. Each raindrop that falls is a reminder that the water cycle is ongoing, and that the chemistry of rain, its journey from evaporation to precipitation, helps to keep the planet alive and thriving. Rain is often seen as a simple, natural occurrence, a cycle that takes place beyond our control. However, for those who rely on the land for their livelihood, farmers, gardeners, and agricultural workers, rain is far more than just an atmospheric event. It is a critical factor in the success or failure of crops, influencing everything from plant health to food security. The relationship between rain and agriculture is one of deep interdependence, with the rhythm of rain guiding the cycles of planting, growing, and harvesting. The role of rain in agriculture is multifaceted, affecting not only the quantity of crops, but also their quality. At its core, rain provides the essential moisture that plants need to grow. Without it, the soil becomes dry, and plants struggle to absorb the nutrients necessary for survival. But rain is not just about water, it is also about timing. The amount, frequency, and timing of rain can mean the difference between a bountiful harvest and a crop failure. When rain falls in the right amounts at the right time, it creates optimal conditions for plant growth. During the early stages of crop development, moderate rainfall helps to establish strong root systems. As plants grow, consistent rainfall ensures that they receive the moisture they need to continue developing, producing leaves, flowers, and fruit. In turn, healthy plants provide food, fiber, and other essential resources for humans and animals alike. But the timing of rain is crucial. Too much rain can be just as detrimental as too little. In regions where rain is abundant, heavy, rainfall can lead to waterlogging, where the soil becomes oversaturated and oxygen is displaced. This prevents plant roots from breathing, stunting growth and potentially suffocating the plant. Crops like rice, which thrive in flooded conditions, can tolerate more water, but most other plants, including wheat, corn, and vegetables, require a delicate balance of moisture. When heavy rains arrive during the growing season, they can flood fields, wash away seeds, and even lead to erosion, stripping away the topsoil that holds vital nutrients. On the flip side, drought, or the absence of rain, presents another significant challenge to agriculture. Drought occurs when rainfall is insufficient to meet the water needs of plants. Without adequate moisture, crops cannot grow properly, and the soil begins to dry out, losing its fertility. For farmers in regions prone to drought, the consequences can be severe. Crops fail, and water sources become strained. In some cases, drought can lead to desertification, where once fertile land becomes arid and unproductive, further compounding the difficulty of agriculture. This delicate balance between too much and too little rain is a constant concern for farmers. In many parts of the world, irrigation systems have been developed to provide water during dry periods, ensuring that crops continue to grow even when rainfall is sparse. However, irrigation is not without its challenges. In regions where water is scarce, over-reliance on irrigation can deplete water resources, leading to competition for water between agriculture, industry, and local communities. Farmers have long had to adapt to the rhythms of rain and drought, using techniques that help manage and conserve water. In many cultures, traditional methods of water management, such as terracing, rainwater harvesting, and the construction of ponds and canals, have allowed communities to thrive in areas where rainfall is unpredictable. These methods not only store water, but also regulate the flow, ensuring that it reaches the crops in the right amounts and at the right times in the modern world. Technology has provided new tools to better manage rainfall's impact on agriculture. Weather forecasting has become an essential part of modern farming, allowing farmers to predict when rain will fall and plan accordingly. Drought-resistant crops have been developed, designed to withstand periods of dry weather, ensuring food security in areas where rain is less predictable. Innovations in irrigation systems, such as drip irrigation, help to conserve water while providing crops with the moisture they need. Yet despite technological advances, rain remains the most unpredictable factor in agriculture. The global climate crisis has only intensified the challenges farmers face. As temperatures rise and weather patterns shift, the once predictable cycles of rain and drought have become more erratic. Some regions are experiencing more intense rainfall and flooding, while others are grappling with prolonged dry spells and water shortages. The unpredictability of rainfall now threatens the stability of global food systems, raising concerns about food production, prices, and access to essential nutrients. For all of rain's unpredictability, its role in agriculture remains indispensable. It is the heartbeat of the Earth's agricultural systems, nourishing plants, replenishing the soil, and ensuring the continuation of life. The relationship between rain and agriculture is a dynamic one, where farmers, crops, and the environment all interact in a delicate balance. When this balance is maintained, agriculture flourishes. But when disrupted, the effects ripple through ecosystems and human societies alike. In a world increasingly impacted by climate change, understanding and adapting to the changing patterns of rainfall will be essential for securing the future of agriculture, whether through advanced technology, sustainable farming practices, or a deeper understanding of the water cycle. The goal remains the same: to ensure that rain continues to nourish the earth, providing the resources needed to feed, clothe, and sustain life on the planet. Rain is not only vital for sustaining life today, but it also plays a crucial role in the very origins of life itself. As we look back to the earliest days of the Earth, over 4 billion years ago, we find that the planet was a very different place. Volcanic eruptions, meteor impacts, and an atmosphere thick with gases created a hostile environment. Yet, within this chaos, rain played an essential part in the development of life. Through the chemistry of water, rain helped create the conditions necessary for the birth of life on Earth. One of the most fascinating aspects of rain's role in prebiotic chemistry is its ability to dissolve and carry various compounds that form the building blocks of life. In the early Earth's environment, rain was much more than just water falling from the sky. It was a delivery system for vital chemicals, including amino acids, nucleotides, and other organic molecules that would later form the basis for life. The story of life's origins is intimately tied to the presence of liquid water. Scientists believe that water was essential for creating the first complex molecules needed for life. Rain, which brought fresh supplies of water from the atmosphere, acted as a conduit that allowed these molecules to combine and form more complex structures. This process, known as abiogenesis, is the theory that life arose from non-living matter through natural chemical processes. In the primordial world, rain could have facilitated the formation of the first amino acids, the building blocks of proteins, by combining simple gases like methane, ammonia, and hydrogen with water. These gases, present in the early atmosphere, would have been swept up by rain, allowing them to interact in ways that could lead to the creation of more complex molecules. Just as rain carries essential nutrients and minerals to modern ecosystems, it may have transported the raw ingredients needed to jumpstart the process of life. The famous Miller-Urey experiment in the 1950s demonstrated how simple chemicals present in the early Earth's atmosphere, when subjected to electric sparks to simulate lightning, could form amino acids. This groundbreaking experiment provided a glimpse into the types of chemical reactions that could have occurred in the presence of rain and energy sources, helping to set the stage for life's emergence. Rain, in its early form, could have provided a stable environment in which these chemical reactions took place. As rainwater fell and gathered in pools or shallow oceans, it would have created ideal conditions for organic molecules to concentrate. These pools of water, rich in dissolved chemicals, could have acted as chemical laboratories where the building blocks of life slowly came together over millions of years. Furthermore, rain may have played a role in the formation of prebiotic chemical soup, a term used to describe the primordial mixture of organic compounds that eventually led to the first living organisms. As rain washed over rocks, minerals, and volcanic landscapes, it could have dissolved key elements such as phosphorus and carbon from the environment, creating the chemical richness needed for life. The minerals and the rocks could have acted as catalysts, speeding up chemical reactions and helping to form the complex molecules that we now associate with life, such as proteins, nucleic acids, and lipids. It is even possible that rain, in combination with the intense energy of lightning and the geothermal heat from volcanic activity, could have created the first self-replicating molecules, the precursors to DNA and RNA. These molecules are central to the genetic processes of life today, carrying information from one generation to the next. In this way, rain's role in the creation of life was not passive. It was an active participant in the chemical reactions that led to the development of the very molecules that underpin all living organisms. As the early Earth began to cool and stabilize, rain likely played an even more critical role in sustaining early life forms. Once the first simple life forms, such as single-celled organisms, emerged, rain continued to support them by replenishing the water needed for their survival. Rainwater would have provided a constant source of hydration, while also carrying nutrients and minerals to sustain these early life forms in their primitive environments. In a sense, rain was the first sustainer of life, not just in the modern world, but from the very beginning. Without the steady supply of water, essential nutrients, and chemical compounds carried by rain, the processes that led to life's formation may not have been possible. The chemistry of rain, from the dissolution of gases to the delivery of vital minerals, helps set the stage for life on Earth, an event that remains one of the most remarkable in the history of our planet today. As we observe the role of rain in sustaining ecosystems and agriculture, it is worth remembering that the story of life began with rain. It was in the primordial waters of early Earth, fueled by rain, that the chemical reactions that sparked life took place. The same rain that nourishes our crops, replenishes our soil, and refreshes the world around us is, in a very real sense, the rain that made life possible. The cycle of rain is not just a modern phenomenon, it is the very foundation of life on Earth. For plants, rain is not just an occasional visitor, it is a lifeline. From towering trees to tiny grasses, plants depend on rain for hydration, nutrient absorption, and overall health. But rain's relationship with plant life is more than just about moisture. It's about timing, frequency, and how it helps maintain the delicate balance between the soil, air, and the plant itself. Water is essential for all plant processes, but it is especially crucial for photosynthesis, the process by which plants convert sunlight into energy. Rainwater provides the moisture plants need to carry out this vital function. Without rain, plants would be unable to absorb carbon dioxide from the air and convert it into glucose, their primary energy source. This energy allows plants to grow, produce flowers, and create the fruit that sustains the animals, humans included, who rely on them for food. When rain falls on plants, it doesn't just hydrate them, it also serves as a vehicle for transporting minerals and nutrients from the soil to the plant roots. Rainwater, especially when it falls in gentle, steady amounts, is able to infiltrate the soil deeply, dissolving the minerals and making them available to plant roots. These nutrients, such as nitrogen, phosphorus, and potassium, are critical for plant growth, influencing everything from root development to flower formation. The benefits of rain to plant growth go beyond just providing moisture and nutrients. It also aids in transpiration, the process by which plants release water vapor through their leaves. Transpiration helps regulate the plant's internal temperature and creates an upward pull that draws water and nutrients from the roots. When rain falls, it temporarily interrupts this process by providing an external source of water, allowing the plant to focus its energy on growth rather than struggling to maintain moisture levels. This can lead to a noticeable burst in plant growth, especially during the growing season, as plants receive a welcome replenishment of water. Additionally, rain's role in soil aeration is crucial. As raindrops penetrate the soil, they break up compacted layers, allowing air to circulate more freely around the roots. This is particularly important in soils that are prone to compaction, such as clay-heavy soils, where the lack of air can suffocate plant roots. By loosening the soil, rain ensures that roots can access both water and oxygen, essential for healthy growth. Without rain, soil can become dry and compacted, limiting plant growth and potentially leading to stunted or dying plants. But it's not just about how much rain a plant receives, it's about the timing and distribution. Too much rain, especially during the flowering or fruiting stages of plant life, can lead to problems like root rot or disease, particularly if the soil doesn't have adequate drainage. Heavy, continuous rainfall can flood the soil, drowning the roots and making it difficult for the plant to absorb the oxygen it needs. This is especially problematic in crops like beans, corn, or potatoes, where standing water can prevent healthy root development and cause fungal infections. On the other hand, if rain is scarce, plants may struggle to survive, as they rely on consistent moisture levels to maintain growth. In drought conditions, the lack of rain can cause plants to wither, their leaves wilting and their growth stunted. In these dry conditions, plants often enter a survival mode, conserving water by closing their stomata, the tiny pores on their leaves, which reduces transpiration but also limits the plant's ability to take in carbon dioxide. Without rain, plants can't photosynthesize efficiently, leading to poor growth and, eventually, death. This is where the relationship between plants and rain takes on a more intricate role. For many plant species, especially those in tropical or Mediterranean climates, rain is often seasonal. These plants have evolved strategies to cope with the dry periods, relying on the brief, intense bursts of rain that fall during their wet seasons to carry them through the dry months. Some plants, like certain cacti and succulents, have developed the ability to store water in their tissues, allowing them to survive longer without rain. Others, like seasonal crops, have adapted to grow quickly during the rainy months, completing their life cycle before the dry season begins. In the agricultural world, farmers have long relied on rain-fed agriculture, where crops are planted in the hope that seasonal rains will provide the moisture necessary for growth. While modern irrigation systems have reduced the dependency on rain, especially in drier regions, rain remains a critical factor in the success of many crops, particularly in regions where rainfall is reliable and abundant. For these farmers, the timing of the rains is everything. Too early, and the soil may become waterlogged, affecting seedling growth. Too late, and crops may not reach maturity before the dry season sets in. The importance of rain for plant growth goes beyond just agriculture. In forests, rain nourishes trees that provide shelter, oxygen, and food for countless species. In grasslands, rain supports the delicate balance of grasses and herbivores, maintaining ecosystems that sustain a wide variety of life. And in wetlands, rain fills critical habitats that support species of plants and animals adapted to moist environments. In a world increasingly affected by climate change, rain's role in plant growth is becoming more unpredictable. Shifts in weather patterns, prolonged droughts, and more intense rainfall events are already having significant impacts on global agriculture. As rainfall patterns become more erratic, it becomes even more crucial to understand how plants respond to changing conditions and how to manage rainwater efficiently to protect crops and ecosystems. In essence, rain is the cornerstone of life on Earth. Its influence on plant growth is profound, ensuring that forests, crops, and wild plants continue to thrive. Every drop of rain that falls is part of a complex and dynamic system that sustains the life of plants, animals, and humans alike. It is through the rhythm of rain, its ebb and flow, that the cycles of nature continue to turn, fostering growth, maintaining ecosystems, and nurturing the world around us. Rain has always been more than just a weather event. It is a profound messenger of life, carrying with it not just water, but the potential for growth, transformation, and renewal. Each raindrop that falls from the sky is a silent bearer of nature's will, a small miracle in itself. But when combined, these drops create a symphony that sustains the earth. From the smallest plant to the largest animal, rain brings nourishment, sustains ecosystems, and revitalizes the land. It is, in every sense, the very pulse of life. At the most basic level, rain is an agent of renewal. It breathes life into parched landscapes, turning brown fields into lush, green meadows. In deserts, rain is an event so rare and precious that it transforms the landscape into a temporary oasis, allowing flora and fauna to flourish before the dry season returns. In forests, rain sustains the delicate balance between trees, shrubs, and the intricate web of life that thrives beneath the canopy. Every droplet that falls carries with it the nutrients and minerals necessary to support life on Earth, turning barren soils into fertile ground, ready to nurture the seeds of tomorrow's crops, flowers, and trees. But rain's role in nature goes far beyond just providing water. Rain is a communicator, bringing with it messages that reverberate through ecosystems. The first rains of the season, after a long dry spell, are often celebrated by plants, animals, and humans alike. In many cultures, the arrival of rain is seen as a sign of hope, prosperity, and renewal. It marks the changing of seasons and is seen as a harbinger of growth and abundance. For ancient civilizations, the coming of rain was a divine message, a gift from the gods that promised a bountiful harvest and continued life. In some parts of the world, the sound of rain is a familiar and cherished rhythm, signaling life's persistence against the odds. It brings with it the ability to connecting the air, the soil, and the living organisms that rely on each other for survival. As rain nourishes the earth, it simultaneously supports the life that inhabits it, fostering relationships between plants, animals, and humans. The roots of trees drink in the water, while insects, birds, and mammals alike benefit from the lush growth that follows. Rain's arrival is a gentle reminder that life is in constant motion, a cycle that requires both patience and resilience. Rain also carries a deeper message about interdependence. As it falls from the clouds, it carries within it the essence of the atmosphere, particles, gases, and traces of everything it has passed through. As it hits the earth, it does not just nourish the soil. It transports nutrients, minerals, and even microscopic life forms to new areas, spreading the potential for growth far and wide. The rain can carry seeds to new lands, facilitate the movement of pollen, and distribute organic matter in a way that ensures the health of ecosystems across regions. It's in the quiet moments after rain that we often feel most connected to nature. After the storm, when the air is fresh and the world smells of earth and growth, there's a palpable sense of harmony. The earth seems to take a deep breath, renewed and refreshed. This is rain's true gift, its ability to reconnect us to the natural world, to remind us that life, in all its forms, is an intricate web of cycles, each one relying on the other for survival. Rain's message is one of continuity. Every time it falls, it brings life to the land, nurtures plants, and helps maintain the fragile equilibrium of ecosystems. It is through rain that ecosystems remain vibrant and life continues to thrive. Without it, the balance would be lost. So, rain does more than provide water. It is a messenger that tells the story of survival, growth, and connection. It brings life back to the land, replenishing what was once lost and ensuring the continued health of the Earth's natural systems. In this way, rain is a symbol of nature's resilience and strength. No matter how many times the land dries out, rain will return to restore and renew it. It serves as a reminder that even in the darkest of times, growth is still possible. The message is simple: life continues, and the Earth's cycles, though at times interrupted, are always ready to begin again. Rain also carries with it the quiet reminder of our own connection to the Earth. As we receive the nourishment from rain, we are reminded of the role we play in sustaining the balance of nature. We too are part of the intricate web of life, and like the plants and animals around us, we depend on rain for survival. It's in this mutual reliance on rain that we understand our place in the larger picture, and it's this connection to the earth that enriches our lives. Every time the sky darkens and the first droplets begin to fall, we are reminded that rain is not just an event, it is a profound communicator, a bearer of life, and a symbol of the cycles that sustain our world. Through the rain, nature speaks to us, urging us to appreciate the gift of life and the interdependence of all things. Rain, while seemingly simple, carries a chemical signature that reflects the environment it falls in. Each raindrop is a unique record of the atmospheric conditions it has passed through, the particles it has collected, and the gases it has absorbed on its way to the earth. This chemical signature, though invisible to the naked eye, tells a fascinating story about the air, the soil, and even the creatures that inhabit the environment. One of the most notable components of rainwater's chemical signature is its pH level. Pure water, theoretically, has a neutral pH of 7. However, rain is rarely pure. It's influenced by the gases, dust, and other particles in the atmosphere. In general, rain is slightly acidic with a typical pH between 5.0 and 6.0. This slight acidity arises from the interaction of water with carbon dioxide CO in the air, which dissolves into the water to form carbonic acid H. While this level of acidity is harmless to most living organisms, it plays a role in the natural processes of soil fertility and plant growth, helping plants absorb minerals more efficiently. That the presence of sulfur dioxide, SO, and nitrogen oxides NOx in the atmosphere can lower the pH even further, leading to acid rain. When sulfur dioxide and nitrogen oxides combine with water vapor in the atmosphere, they form sulfuric acid and nitric acid, respectively. These acids can significantly lower the pH of rain, making it more acidic and capable of causing damage to the environment. Acid rain has been responsible for eroding statues, damaging crops, and harming aquatic ecosystems. However, rain that falls in urban areas or near industrial zones tends to carry a more pronounced acidic signature, influenced by pollutants from cars, factories, and other human activities. Another key element of rain's chemical signature is the presence of minerals and trace elements. Rainwater, while it might seem to be just water, often contains dissolved minerals that it picks up as it passes through the atmosphere. These can include calcium, magnesium, potassium, and sodium, which are essential for the health of plants and ecosystems. These minerals can come from a variety of sources: the ocean, dust storms, volcanic eruptions, or even the breakdown of rocks and soil. These minerals are carried by rain to the earth, enriching the soil and contributing to the fertility of the land. In areas with a lot of industrial activity or heavy traffic, rainwater may carry higher concentrations of pollutants, like heavy metals, including lead, cadmium, and mercury. These substances are harmful to plants, animals, and humans, accumulating in ecosystems and potentially contaminating water sources. This chemical signature can offer clues to scientists monitoring the levels of pollution in an area, providing a valuable tool for environmental analysis and public health initiatives. In contrast, rain falling over more pristine environments, such as remote forests or mountain ranges, often carries a much cleaner signature. Here, the mineral content is lower, and the water may have a more neutral pH. In these areas, the rain helps to replenish the soil with essential nutrients without the contamination from industrial pollutants, contributing to the health of natural ecosystems. For scientists studying ecosystems, analyzing the chemical signature of rain can provide a wealth of information about the health of the environment. Interestingly, rainwater can also carry biological tracers, microorganisms such as bacteria, viruses, and fungi that it picks up as it falls through the air. These microscopic life forms can travel vast distances through the atmosphere, only to be deposited with the rain. In some cases, these microorganisms can even influence the ecosystems where the rain falls. For example, certain fungi and bacteria play an essential role in the breakdown of organic matter, contributing to the nutrient cycling in ecosystems beyond. These more typical components, rainwater can also pick up organic compounds from plants and animals. As rain falls through forests or fields, it may absorb plant oils, pollen, and organic particles from the air. These compounds, while invisible, can have a significant effect on the local ecosystem. For example, when rain falls in areas rich in plant life, it can carry compounds like terpenes and phenols, organic molecules that plants release into the air. These compounds can serve as signals for nearby plants and animals, triggering growth responses or influencing plant-pollinator interactions. In some cases, the organic molecules carried by rainwater can even affect the local weather, influencing cloud formation and precipitation patterns. Rain also plays an important role in removing dust and pollutants from the atmosphere. As it falls, raindrops trap and carry particles like dust, soot, and ash, removing them from the air. This washout effect helps to improve air quality and reduce the impact of air pollution, especially in urban areas. After a rainfall, the air often feels fresher, clearer, and more breathable, as rain has effectively scrubbed the atmosphere clean. This ability of rain to remove particles from the air is an important natural process, contributing to the overall health of the environment. In essence, the chemical signature of rain is a reflection of the world it interacts with. Each raindrop carries with it a record of the atmosphere it has passed through, the pollutants and minerals it has collected, and the biological life it has encountered. For scientists, rainwater is a powerful tool for understanding environmental conditions and changes in ecosystems. For the rest of us, it's a reminder that rain is not just a source of water, it is a messenger, carrying the history of the sky and the earth within every drop that falls. Rain is much more than just a natural phenomenon. It is a symbol of renewal, hope, and the promise of life. Every drop that falls from the sky carries with it the potential for growth, the ability to nourish, and the chance for ecosystems to flourish. Once more, the promise of life in rain lies not only in the replenishment of water to the earth, but also in the deep connections it fosters across time. From the origins of life on Earth to the present day, rain has always been essential to life's continued existence. From the moment water began to condense and fall on a young, barren Earth, it set in motion the chemical processes that would eventually lead to life's birth. Early Earth's atmosphere was hostile, with extreme temperatures and a lack of liquid water, but as rain began to fall, it helped shape the planet's surface, carving out rivers and lakes and enabling the emergence of life. It's in this early rain, this ancient cycle, that the foundation for the evolution of all life on Earth was laid. The promise of rain is also reflected in the way it sustains life today. From the smallest microorganisms to the largest mammals, every living thing relies on rain in some form to survive. In plants, rain delivers nutrients and hydration, ensuring their growth and development. Without rain, forests, grasslands, and crops would wither away. Unable to carry out photosynthesis, the process that produces the oxygen we breathe. Rain enables the water cycle, which replenishes our rivers, lakes, and groundwater, providing fresh drinking water for billions of people. Without this cycle, life as we know it would not exist. Beyond its role in sustaining life, rain has the ability to bring people together. In many cultures around the world, rain is a symbol of fertility, prosperity, and connection to the natural world. In agricultural societies, The arrival of rain is a moment of relief and joy, signaling that crops will grow and the harvest will be plentiful. For indigenous cultures, rain has been viewed as a sacred gift, with rituals and prayers made to honor the forces that bring it. Across generations, communities have celebrated rain, recognizing its deep importance for their survival and well-being. Rain also serves as a connector between ecosystems, regions, and even countries. Water doesn't belong to any one place, it moves across the world, joining distant rivers, lakes, and oceans. Through the global water cycle, rain is part of a never-ending journey that links all living things, from the lush forests of the Amazon to the arid deserts of Africa. Rain connects diverse ecosystems, ensuring that nutrients flow and life persists in every corner of the planet. No matter where you are in the world, the rain that falls is a reminder that we are all part of a larger, interconnected system, a system that sustains life for all species. The promise of rain is evident in the way it nurtures ecosystems, but it's also found in the resilience of life. In times of drought, when landscapes are parched and rivers dry up, rain becomes a precious commodity. It may come as a storm, an unexpected gift that temporarily relieves the suffering of the land. Yet even in the harshest conditions, life finds a way to endure. Some plants have evolved to withstand long dry periods, storing water in their roots, stems, or leaves, while animals may migrate in search of rain-soaked regions. The promise of life in rain is that, no matter how dry the land becomes, there is always the potential for recovery, provided the rains return in the context of climate change. The promise of rain is increasingly uncertain. Shifting weather patterns, rising global temperatures, and changes in atmospheric circulation are causing unpredictable rainfall patterns. In some regions, rainfall has become more intense, leading to devastating floods, while in others, prolonged droughts have left once fertile lands barren. This growing unpredictability in rain's patterns poses a challenge to agriculture, water resources, and ecosystems around the world. Yet even in the face of uncertainty, rain remains a symbol of hope. In a world that often feels unpredictable and divided, rain is one of the few natural forces that unites us all. When it falls, it refreshes the earth, bringing with it the promise of renewal. It may wash away the dust of the day, clear the air, and nourish the soil, but it also brings with it the potential for a fresh start. Whether it's a farmer's field ready to sprout, or a parched desert springing to life, rain carries the promise of life in its wake, reminding us that growth and healing are always possible. For future generations, rain's promise is not just a gift to the planet, but a responsibility. As we face the impacts of climate change, it is up to us to protect the water cycle, manage water resources sustainably, and ensure that this life-giving force remains a constant in our world. The promise of rain is one that transcends time, reminding us that, while life may sometimes be challenging, the rains will always return, bringing with them the promise of renewal and the hope that life will continue just as it always has. In every raindrop that falls, there is a story of survival, of connection, and of promise. The rain is the great nurturer of the planet, sustaining life in all its forms, linking the Earth's ecosystems, and offering the chance for growth and rejuvenation. It is a message of life itself, timeless and ever-present, waiting to fall again. As we stand beneath the sky, whether drenched by a soft shower or caught in the intensity of a thunderstorm, we are witnessing a natural marvel that has sustained life on Earth for billions of years. Rain is not just a weather event, it is a vital force, a messenger of life, and a carrier of stories from the heavens to the ground. It has shaped the planet's landscape, nourished ecosystems, and fueled the growth of every living organism. From the early days of Earth, when rain first began to fall and create the conditions necessary for life's origins, to today, where it continues to play a pivotal role in the cycles of agriculture, climate, and biodiversity. Rain is an essential part of the story of life. Every droplet that falls from the sky carries the potential for renewal, growth, and transformation. It replenishes the soil, nourishes plants, cools the air, and refreshes the earth in ways that are often invisible yet infinitely powerful. Rain is more than just a source of water. It is a symbol of resilience and hope. For the plants that depend on it, rain is a lifeline, a momentary reprieve from dry spells and harsh conditions. For ecosystems, it is the breath of life, cycling through the natural world, ensuring that nutrients are replenished and that balance is maintained. For farmers and communities around the globe, rain is a promise of survival, a signal that the cycle of life will continue, that food will grow, and that ecosystems will thrive. But beyond its physical impact, rain carries with it a deeper, almost spiritual significance. Throughout history, humans have connected rain to divinity, fertility, and the cycles of the earth. Cultures worldwide have celebrated rain as a gift from the heavens, a blessing that marks the changing of seasons, the fertility of the soil, and the abundance of life. Even today, rain serves as a reminder that we are part of something larger, an interconnected world where water is not only a resource, but a lifeblood that sustains every living thing. Yet, in an age of climate uncertainty, the story of rain is also one of adaptation. As we face the challenges of a rapidly changing climate, understanding rain's rhythms and embracing sustainable practices is crucial. We must recognize the fragility of this vital resource, ensuring that we respect and protect the natural processes that govern it. The future of rain and the future of life on Earth depends on our ability to balance human needs with the delicate cycles of nature. The science of rain has brought us closer to understanding the atmosphere, the water cycle, and the many forces at play in shaping our planet. From the chemistry of condensation to the physics of raindrop formation, every detail of rain is an intricate marvel. But perhaps the most profound lesson of rain is that it is both a gift and a responsibility. It teaches us that, despite the forces of nature beyond our control, we hold the power to influence how we interact with the earth, to care for it, nurture it, and ensure that future generations inherit a planet where rain continues to fall, nourishing the land and life in perpetuity in the end. Rain reminds us that no matter how turbulent the storms or how dry the seasons, life always finds a way. It is a cycle of renewal that repeats, time and again, as long as the earth spins beneath our feet. And with every drop that falls, rain carries the timeless promise of life, a promise of growth, connection, and hope for the future. Rain is more than just water from the sky. It is a symbol of life itself, an eternal rhythm that ties us to the planet and to each other. And in its quiet, constant falling, it tells the greatest story of all, the story of life, ever flowing, ever renewing, and ever growing.